Hello, everyone. It's a great pleasure to welcome Mandeep. Mandeep and I, we met in Kenya, in Crete, because Daniel and I had started an ITN project with many other people, including some people from London, but which actually prefer Crete and Kenya. And they organized a conference there. And Mandeep couldn't come right away to the lab to start his PhD, but he could come to Crete. So we welcomed him in Crete. So somewhere, maybe in the depths of someone's computer, there is a movie of me dancing the sirtaki with Mandeep. Uh, but well, it was a good start. And then Mandeep did a brilliant PhD thesis with Daniel. Afterwards, he went to work with Detlef and Youssef and Betzal and all that. But he kept working with Stefan. It was a nice moment in his collaboration with Detlef. And also, he did something that we're all curious about. I think we're all curious about, which is Marangoni forces in Basilisk. And so you will tell us more about that.
So I'll put a general topic which is numerical simulations of inkjet printing. These are all the collaborators. So as you said, Stefan was working with me for this. I'll go quickly to the context. So apart from classical printing that you have printing on paper, there are several other applications of depositing drops. For example, 3D printing or printing of micro lenses. In biology, you have monitoring of gene expression and printing of biological tissue. So you can do uh, these kind of things with inkjet printers. And if you look at the inkjet printer, you can break the dynamics into 7 fundamental problems that you can see here. So you have to inject ink through a nozzle that makes a jet. This jet will break into droplets. You impact this droplet on a substrate and then you dry them and they form a print that you desire. And here first I'll focus on the problem 4, which is the breakup of this jet that is created in the inkjet. Some experiments were already done in the lab with respect to this using a micro drop setup. So it's not exactly inkjet, but they were generating jets of water. And what they found is at certain driving condition, you can produce this kind of breakup where you have a head droplet followed by a tail droplet, which is what is referred as satellite droplet, which can be bad for printing. And moment you add some amount of polymer, you see that this tail droplet remains attached to the head droplet. So you suppress the second breakup that happens there. Also that this jet is a bit slower than the first one. If you add a bit more polymers, you can reach a situation where you don't have breakup altogether and this jet retracts back into the nozzle. So one of the questions that we asked is what are the parameters that control this kind of behavior. We have more complementary experiments on actual print head. There I show you different driving conditions. So the dynamics is in this direction. And what we see is that depending on different voltage, you can have different kind of jet. But these pictures are captured with stroboscopy. So each frame is not the same experiment, but the frame after is a different experiment from the previous frame. And if you see here, even in this well-controlled experiments, you see drops at different location appearing and disappearing, which means that these experiments are not highly reproducible, even if you keep everything else same. So during the breakup, even in experiments, it's hard to reproduce what they have been seeing. So I'll come back to this, what can cause this. First, let me describe you what is the model that we use for inkjet printer. So we have an ink reservoir from where the ink will flow into a chamber where we have an actuator that pushes the ink out of the feed through and then through the nozzle where we have the jetting. And we have some models that are already available in literature which are based on lumped element models where we model different components with the spring, mass, damper, which are connected in series or parallel. And in numerics, we have we have a 1D warm sleeve flow in the restrictor, from where the ink can flow into an ink chamber, for which we solve a pressure ODE. So this converts a pressure signal, sorry, a voltage signal into pressure signal, and takes into account what is the inflow and outflow of ink along with what is the compliance of the chamber. And from there on, we have feed through and nozzle, and outside the nozzle flow, for which we solve the Navier-Stokes equations using Basilisk. We have these extra stresses, sorry. So we have these extra stresses in Navier-Stokes which come from the viscoelastic nature of the ink, for which we use Allroyd B model, where the stress is related to conformation tensor linearly, and this conformation tensor A follows a relaxation equation which is given here. There are two sort of independent parameters that you get out of this model, which is polymeric viscosity and relaxation time, and the ratio of two is often referred to as a shear modulus as well. So with these two parameters, you can try to mimic what is happening when you add polymers into the system. So first we try to validate our code or simulations, because we have this extra code on 1D dynamics inside the restrictor, etc. So we validate this with already available finite element code for a Newtonian case, and we see that we can reproduce very well the chamber pressure and the dynamics that we see in the other numerics. We also compare with some experiments. So this is an actual print head, and I show you again how this jet forms and what is the length of this jet, or how does the tip of this jet evolves in time. So we can reproduce well the experiments as well with this kind of modeling. But the breakup still remains different in these two situations, and one of the, as I told you earlier, that even in this case the breakup is not reproducible even in the experiments. And one of the reason we could find out was that if you put a contact line model that depends, that can change breakup a bit. So this is the conclusion of this slide, but I'll show you already this results here. So you have these three interfaces which are different boundary conditions. So one is pinning, one is slip with a constant contact angle of 90 degree, and another red one is a precursor film, and this is zoom of this area. And you will see that at short times, even though all the dynamics look very similar, apart from of course very close to the solid, the jet itself remains looks very similar, but when the at longer times the lengths are different, but not just that, the breakup can be different because of just changing a boundary condition. So it's a very sensitive case to the boundary condition. And what we do is we still argue that phenomenologically most of the things are similar, and we try to understand more the details of simulations by using a pinning boundary condition, and try to go back to this situation, that can we reproduce this situation in the numerics. And turns out that okay, I fix already several parameters like the geometry of the print head, etc., the driving pulse, and what I vary is only the parameters that control the viscoelasticity of the ink. So I vary the non-dimensional elasto-inertial number, which is ratio of the shear modulus to rho u square, which is the driving pressure, and the Deborah number, which is the time it takes for the polymers to relax as compared to a typical time scale of jetting. And if I do so, I can basically reproduce what we see in the experiments, that in certain regime you have the jet that elongates, but it doesn't break up, but it retracts back into the nozzle. Whereas in some case you have a drop which remains attached to the tail droplet, so that you suppress the secondary breakup, whereas here you have multiple droplets and you could not suppress the secondary breakup. And if you look in phase map of elasto-inertial and Deborah, you can see that for small elasto-inertial numbers, you have situation 1, and medium, you have situation 2, and for large elasto-inertial number, you have situation 3, independent of the Deborah number. So if your Deborah is larger than 1, independent of Deborah number, you have this transition at horizontal line. So even if you understand one of these transitions, you can figure out what is happening in the other cases, right? So to understand this, I break the problem further in 3 time scales. So first is what happens inside the nozzle before the jet comes out. And here I show you the length, the distance of the tip of the jet as a function of time. So inside the nozzle, nothing much changes when you add polymers, because these polymers are known to play more role in extensional flows as compared to shear flows. So this was seen in experiments as well. So this is relatively boring case. But when it comes out of the nozzle, you see that the extension is different. So this length is behaving differently. And after that, the third time scale I will focus is the breakup time scale. So how does this breakup happens? So let's go to the first problem, which is the extension of the jet as it comes out of the nozzle. For this, I do some energy analysis. So you have important energies in the system, which is kinetic energy, the surface energy, the viscous dissipation, and the elastic energy, and they are conserved. I look at an ideal system where there is no dissipation, and I write the energy in transport form, which I can integrate in time, and I can have an evolution equation for kinetic energy. I further assume that we have a cylinder jet, so that the axial variation is much larger than the radial ones, and then I can get a evolution equation for energy, which tells me that the kinetic energy of the jet at time t is nothing but the initial kinetic energy at t equals to 0 plus some influx of energy from the left boundary minus the surface energy and the elastic energy. So these are the energies that you need to integrate over the length of the jet in assuming a cylinder jet. And if I go back and look at my simulations to see what are these energies, so I start with the Newtonian case where there is no elastic energy, and if I plot different energies, I see that so there is a color map also on the right. So I see as the jet extends, there is some influx of energy from the boundary, which creates a lot of kinetic energy of the jet, and as it comes out, this decreases and the surface energy increases, so new surface is created. So you are creating new surface at the expense of the slowing down of this jet, and there is some influx initially, and at some time there is a periodic influx. For example, you will see here, so there is some periodic influx of energy from the left boundary after a certain time as well. Now what happens if you are weakly viscoelastic? So you have this elastic energy, which is still very small compared to the other energies that are there. And you will see from the color maps here, so on the right is the elastic energy color map, that this elastic energy is focused on the regions where there is a lot of thinning. So it's more affecting this thinning than the elongation, so to say. And then in a very strong viscoelastic case, you have this elastic energy, which becomes very much comparable to the kinetic energy, so that it penalizes kinetic energy, and your kinetic energy goes down as this jet reaches maximum, and then it goes in the opposite direction and jet is retracted back into the nozzle. There is some interplay between the kinetic energy and elastic energy that controls this dynamics. So I go back to my cylinder jet model, and then I try to make more approximations on how this jet is extending. So I assume that, okay, this jet is extending linearly such that I can isolate the spatial variation from the temporal one, and I can write the kinetic energy and the surface energy in a simpler way, which will give me a equation for the length or the velocity of the tip of the jet as it comes out of the nozzle. And now if I look back at again the Newtonian case, because this is the reference case, I plot the length of the jet as a function of time. I see that this L dot is sort of constant at long time. So and this constant value is not very far from what was the initial L dot as the jet came out of the nozzle, right? So therefore, what I argue is that these terms are relatively less important as compared to these two terms, and a very simple model like this for the Newtonian case is not very bad in predicting at least the length or the tip, how it evolves. But what about the elastic energy? So we can also look into the elastic energy of the system. In elastic limit, which is large Deborah, which is where we are, we can work in Lagrangian framework, and the conformation tensor is finger tensor times its transpose, where finger tensor is nothing but deformation principal axis. So what I mean is, if you have a cylinder which is full of polymers, and if you stretch this cylinder, you have some deformation, and with this you can write deformation conformation tensor as ratio of length in each direction, and the elastic energy is nothing but the trace of this. So you have this formula for elastic energy, but there is a problem because here you assume that you are in equilibrium state. So there is a fitting parameter LE that you need to figure out what is there, because in jet there is no equilibrium state that we start from, right? So to do so, I try to fit data in the simulations for these simulations that I showed earlier. And if I plot here energy compensated with the Young's the shear modulus, you see that for small elasto-inertial number you're already overlapping data well, which was because for small elasto-inertial number there's not big difference in the length of the jet, so this part is relatively less important as compared to this part. But if you take the whole thing by using a LE equals to the radius of the nozzle, you can fit the data better for the elastic energy. And you can do this for the other cases, for example, larger Deborah numbers, and the story remains the same, that if you compensate with this kind of function, you can fit the data relatively better, especially in the first region before the influx. And now this I can put back in the model, and I get a full model which I can non-dimensionalize in terms of elasto-inertial and Weber number. And I get an evolution equation for the length of the jet. Solving this is not very straightforward because it's a non-linear ordinary differential equation, but I can do some approximations as previously for the Newtonian case, that the influx and the surface energy are less important, and that the length of jet is much large compared to the equilibrium, if there was some equilibrium at some point. And then what you get is a simpler equation, but it has all the ingredients that we felt was important, that the length of jet is given by initial like velocity minus some contribution of the elastic energy that takes away the velocity from the jet. And this you can solve by trigonometric substitutions, and you will get that length goes like sine of the square root of 3ei over Le. This I call as L model, right? And then with this you can predict, like, when do you transition from a case where you have so this model will basically tell you that your jet always comes back, but there is a time in which it will come back given by this sine square root of ei, and depending on your ei to Le ratio, you can have transition from the jet when it comes back into the nozzle due to the elastic energy. So when this time is comparable to the breakup time, you have this jet retracting back into the nozzle. So with this kind of model, you can predict when do you transition from jetting to no jetting but a retraction phase. So the model, like I say, different Deborah, but it's for infinite Deborah, so it's the same for all of these cases. But there's one problem with this, because there I again has to fit this LE equals to 0.1 as compared to the previous values that I obtained by just fitting the elastic energy. And now I'll talk about the last phase of the jet, which is the breakup. So this is a problem similar to what people have studied in extensional rheology, that you take two plates and you pull them apart and you look at the bridge that is formed. For a Newtonian case, you will have finite time singularity that breaks up this this ligament. For a fully elastic case, you will always reach a certain height constant, and in case of a viscoelastic fluid, you have this power law. So again, we start with the Newtonian case, and I look at the secondary breakup here. I track the height of the interface as function of time, and we see that it breaks as we approach this delta H, which is 1 grid size. And you can get this scaling by comparing inertia and capillarity, that it goes like T to the power 2/3 to the singularity that breaks it. But when you have elastic stresses, you need to consider them. So you have elastic stress, which is given like this, and you can again write the conformation tensor, but this time in terms of the radius of the jet, or radius of the ligament. So you get a conformation tensor like this, and you can get the stresses which are due to the polymers. And again, we have a fitting parameter here, which is Re, because there is again no equilibrium that we start with. And I assume that the jet is compressed much larger than the equilibrium radius. And then if you do so, you can again fit the stresses well from the simulation. So here the simulations are dotted lines, and the solid lines are from the model that I just presented, and you get a fitted value of Re. And then at large Deborah number, this tells you that you will go to a constant height, right? Which was the prediction from the fully elastic theory. And what I show you here is now what happens when you add polymers to the system. So let's first look at this red color curve for elastic EI 2 minus 5. You see that this jet thins, it sort of reaches a plateau, and then it breaks up. So this is here, so it sort of reaches a constant value, and then it breaks up. If you increase now the elastic inertial number, you again thin, you will reach a constant thickness for some time, but then this breaks up again. And then in the last case, you reach a thickness, and then this pulls back, and your head droplet remains connected to the tail droplet. Mind you that this breakup, like this thickness is 10 to the power minus 1, and your grid size is 10 to the power minus 3. So it's much resolved, very resolved, this thickness. Even then you have breakup. And if you go back to the elastic theory and compare the elastic stresses to the capillarity, you have you can obtain a constant height of the interface that you will obtain for depending on the elastic inertial number, and this height matches well with the plateau that you were trying to go to. But all of a sudden you have this another solution that it breaks up or goes down, and this puzzled us for some time. But then I think this is because of this problem that we have here, that we are in a large Weber number regime. So these are some simulations from Fentelos and J for the large Deborah number but finite Weber number. So there also they found that they go to some bridge thickness, but then surface tension kicks in, and then you have this bridge becomes unstable and you make bead on a string structure where this bridge collapses into smaller droplet, and then there's a cascading effect that this will happen same to this bridge until it breaks. So the point being that okay, if the breakup in simulations is of course numerical one, because the Allroyd B model doesn't predict breakup at the first place, but it's not because we were not able to refine enough to represent the bridge well that is there in the elastic limit, but it's because of this limitation that we could not resolve well the bead on string instability that would come as outcome of later dynamics at large Weber number. And then there I would end the first part, which was about jetting, and I'll go to the second part, which is on the Marangoni flow solver, which is problem 6-7 here. So when you have evaporation, you can generate Marangoni flows, and we want to study these kind of Marangoni flows using Basilisk. We published this article recently with Stefan in Journal of Computational Physics on this, and the idea is to implement a integral surface tension formulation in volume of fluid method for applications to Marangoni flow. For some other applications, you have this tears of wine that appear because of Marangoni flows, or you have evaporation of droplets, multi-component droplets, where you can generate evaporation driven or even the solutal concentration driven Marangoni flows. The key idea is to implement integral surface tension formulation in volume of fluid, which is the new thing about this. So we have a classical volumetric formulation where the surface tension is added as a singular force with a delta function. This was proposed by Breckbill et al. And then the other idea is that you can represent surface tension as a line force. So you just need to integrate across the line. So it's sigma times dt, where t is the tangent vector, and what you need in discrete form is these tangent vectors at the edge of your control volume or the cell, and what is the surface tension constant there. And then you can add this to Navier-Stokes by using a continuum surface stress model. There are pros and cons to both. On the volumetric side, you have arbitrary thickness that you have to put in to inculcate the delta function, whereas there we don't put this. It's not necessarily conservative, whereas if you see this formulation, it's discretely conservative because there's a neighboring cell with the interface and tangent in the other direction, so you cancel out the contribution, and it's globally and locally conservative. For the Marangoni terms, we have to calculate this surface derivative of the surface tension coefficient in this case, whereas in this case it naturally extends to Marangoni because you can have different surface tension coefficient at the edge points. This can be, we can obtain a well-balanced formulation if we choose some discretization for delta C, whereas in this case we are not sure that we are always well-balanced. This is easier to do in 3 dimensions, like easy to extend, whereas for this case we still don't know how to do it, and we are working on this. Nevertheless, we were convinced that this is a better formulation and we should try to implement this in Basilisk. And for this we have the scheme that was already developed by Al Saud and Stefan a long time ago. So this was for front tracking methods, and this was for level set, and we were trying to extend this to volume of fluid. I'll take some water. So in this scheme, we write the surface tension stress tensor as it has diagonal terms and non-diagonal terms, which are given at the cell center and the vertex center. And to write this, we do a simple exercise of writing the contribution due to the pressure gradient and surface tension in a control volume like this, where you have an interface that cuts a control volume at points A and B. So it's nothing but the pressure difference plus, as I told you earlier, the gamma times the tangent vectors dot x. But you have to be careful because this pressure, it is not constant everywhere. It is jumping due to the Laplace. So you have to take an average of this pressure. So it's P in this side times this length plus the jump in Laplace times this. And similarly for the other cell, you have to do the same. And this you can generalize by defining surface fraction. So it is nothing but the fraction of non-reference phase that is wetting the cell phase. So if you do this, you can write this contribution more generically, and you can put this back in the equation on top, and you can isolate the pressure part and the part that appears due to the surface tension, and you can write this as the difference in the diagonal terms or diagonal elements of the stress tensor. So you derive the diagonal element, and for the non-diagonal terms, we look at a control volume like this, where you have interface that now cuts the horizontal faces, and in this case it's relatively simpler because we are defining this at the vertex center, so there is no jump of pressure, and then you have the non-diagonal term, which is simply gamma t by delta, and this is how the full tensor would look. So you have the diagonal terms and the non-diagonal terms, and if you take divergence of this, which is discrete divergence, you can write the contribution from the surface tension terms in your simulation. So this depends on 3 of the geometric parameters. So you need to evaluate what is the tangent vector, what is the curvature, and what is the surface fraction. With these 3, you can write this tensor, and you can take divergence, and you can write the contribution due to surface tension. And how do you do this from volume of fluid? So we had developed 3 approaches to do this. One is a coupled level set volume of fluid method. So we say we couple the sign distance function with the volume of fluid, and we do it as follows. So we have a sign distance function that is advected along with the VOF, and then this is coupled to VOF by weighting equation, which is this. And we also need to correct for sign distance function using this equation, and once we have a corrected sign distance function, we use this to evaluate the tangent, the curvature, and the surface friction, from where we get the surface tension stress tensor. So in this approach, there is only one downside, that this redistancing takes a bit of time and calculation effort. So we were keen on developing faster algorithms as well. So we also tried a height function method, where we use directly the height functions to evaluate these geometric terms that I said. So we have height functions, which is nothing but integration of the color function in vertical direction, but you can do the same in horizontal direction. So you can have 2 representation of height functions, and depending on where this interface is oriented, we use either horizontal or vertical height functions to calculate the curvature and the tangent, and we calculate the surface fraction by both the approaches, and then we try to do a weighting of the surface tension tensor with these 2 weights that are obtained by vertical and horizontal height functions, and we write a surface tension tensor, which of course gives you the surface tension force. And the last method is the height function to distance method, where we use a sign distance that we now calculate from height function. So we do not need to redistance in this case as well, because we use height functions to write this as sign distance. And how we do this, again, we have two approximations of height functions. We fit these two with a parabola in both directions, and then we make a Newton type iterative method to calculate minimum distance from the cell to this parabola that is represented by height functions, and then we take an average of both x and y approximation, and then what we get is again tangent, the curvature, and the surface fraction with which you write the surface tension tensor and get the method. And then we go on to test these three methods. For the first test case, we have a capillary wave test case where we have a interface that is slightly perturbed, and we look at the dissipation or the decay of this perturbation, and we have solutions which are analytical proposed by Prosperity, and we match with those solutions and we find a good match, and we find order 2 convergence for all the three methods. We also did the test case of rising bubble still at a constant surface tension, so there's still no Marangoni flows in this, and this is a classical case proposed by Heising, where we could look at the rise velocity and the shape of the bubble, and all of them match well with the CSF formulation, which I write as WOF formulation in Basilisk. Then we move to the cases where we have Marangoni flows. So I choose this test case, which is Young, Goldstein, and Bloch. So you have a temperature gradient in which you put the interface. This temperature gradient causes the surface tension to change, and the control parameters in this are the Marangoni numbers, Reynolds number, and the capillary number. And if these three numbers are small, we can obtain the what is the analytically the velocity with which this interface would move under the influence of Marangoni flows, because there's a Marangoni flow that goes from hot to cold, so this interface would move towards the hot side. And this is what we see in the simulations, and we look at the flow field as well as the velocity, the terminal velocity of this drop matches well with the analytical prediction proposed by Young, Goldstein, and Bloch. You already start seeing here that for some methods, for example HF, you have some oscillations that start to appear in the simulations. But it was still better than what we had already with CSF method, which was also implemented in Basilisk by Palas, which showed much more oscillations and also was converging to slightly different solution. Here I show you the speed also. So this is the time it takes for one time step, or it's the average time per time step per number of points. And you see that CLSVOF is relatively slower than the HF and HF2D because of this redistancing function, and this is the total time, whereas this guy, the HF, has more oscillations as compared to the other two. So this is maybe a good trade-off between the three methods. We also use another test case where we have a droplet moving due to the Marangoni flow. So we have hot here, cold there. We have again flow in this direction. The drop goes towards this direction, but this time we have a boundary that stops this drop. And we have one control parameter that we look at is capillary number, which tells you how much this drop can deform. So first I start with the small capillary number. For the CLSVOF method, you get the typical Marangoni rings there. For the HF method, we see that where the oscillations were coming from was related to the point where you shift from vertical to horizontal heights. So this is somehow related to this. And for the HF2D method, you have a similar behavior. And we have prediction of how this drop would slow down. So this is the distance from the wall. As it is approaching the wall, what is the velocity with respect to the Young, Goldstein, Bloch velocity, which was for the bulk. So when you are far away, you approach 1, which is Young, Goldstein velocity, but you slow down with this analytical prediction that was made for capillary number equals to 0. So you match well with this prediction for all three. And last is this test case at larger capillary number. So in this case, as the drop or interface approaches the boundary, it can deform more. And then we have this in all other methods. And there we have some numerical simulations from Ascoli and Lille from long time ago. And then we match with their prediction of what is the velocity as a function of distance and how it slows down, and this matches very well. And with this, I think this is end of the second part as well. So we have implemented a Marangoni solver or integral formulation in Basilisk that extends naturally to Marangoni flows. We have a CLSVOF, which is more accurate but relatively slower as compared to HF, which is less accurate, but then HF2D is in between the two. And then this is first of the kind of method which are both mass and momentum conserving, which is important property for surface tension driven two-phase flows. And with this, I want to thank you, and I'll be happy to answer questions.
What do you think it would be to extend this to 3D?
So I'm trying to think always. I think if you can write on paper, it is not that hard to write in code, but maybe writing on paper is the harder part. Maybe I always talk with Stefan about this, and Stefan, I think he has a better idea on how to write this on paper as compared to me. I think he can maybe answer better how difficult he thinks it is.
So, do you have any idea why function to distance works better than pure function?
So we feel that there are some oscillations in height functions which you dampen when you sort of average and do this procedure of calculating distance. So somehow you have more. So this, why I weight also here is because if I don't weight, I use either or. This already is much worse and I have much more oscillations in this case. So this is height function, right? And when you have HF2D, you somehow do better averaging of the two, which was the main source of oscillations in my opinion in the class when I use only height function method.
Yes. So in one of the test cases, you saw that compared to Pallas, when you compare to Pallas, you converge to a different solution.
No, we converge to analytical solution, whereas he is converging to different solution. So the black curve is the analytical prediction. So with CSF you are converging to, yes. It's, I think it's because he's not putting the correct force that should be there, the correct surface tension that should be there, or force. Basically they are putting force, so he's not putting the correct force which is related to how he calculates this using either the surface gradient of the surface tension or the way you add forces in the CSF formulation.
Not paying attention that the movie you showed at the beginning of the Inkjet with the contact line,
yes.
Also including Marangoni forces?
No.
You do this with Marangoni forces as well?
I think there is everything. It shouldn't be hard to do this. For example, these cases, right? But we were here like really interested in the viscoelastic part because this is special. They have some printing that they are interested in, which uses viscoelastic inks. Yes.
I have a question which is a bit biased. You showed nice comparison with unflip. So why don't you use unflip instead of?
So there are things with respect to OMFLIP. First, for them it was very hard to implement the viscoelastic solver in finite element code. They couldn't do it. They tried for 1 year, so they cannot do viscoelastic things. And then if you see here at longer times the comparison, but this I think they can do. But in these simulations you will see that outside he has assumed that there is a vacuum. So you have slower jet, and when this merge, you have here a drop, a bubble inside your drops where there is no bubbles and things like that. So these intricate details, they can do two-phase, then they become slower, and they are faster with respect to time stepping, etc., because they have a implicit method. But the problem is that they cannot do MPI, and sometimes they have problems with breakup also, because they have to break the finite elements.
Do you have an idea of the time each of the simulation takes?
Yes, so because this is a case where it's favorable for them, and they did the simulations first, so this takes very less time compared to, so this takes, let's say, 13-14 minutes, whereas this takes 3-4 hours on the same machine. That's mostly the time step restriction, because we are explicit, and they can take really big time steps.
Nice that they give such nice result to the last time step.
Yes, because
Do you
there's
have an
no.
idea of the time step they take? How much time?
I think they go at least 100 times what we take.
There would be a
Yes,
sigma CFL sigma would be 100.
100.
Very nice chat. Can I ask, how did you match the viscoelastic property between the experiment and the simulation?
So they measured, and this is the ballpark where they are, but it's a bit tricky because they are somewhere here. So it's close to Deborah 1 and somewhere there. Yes. No, they were doing, I think, the classical thing, whereas what we feel is this is a better way to measure the extensional rheology of the liquids as compared to the two plates, this rheometer, right? Because there you don't have influence of these plates and other things. And also you are faster, so time scales are faster, whereas in this case, it's not that fast. And you cannot measure small relaxation times.
CSF method, in cases where you don't have the Marangoni field, are there any, let's say, limitations on the class number that you can do with your approach opposed to the CSF approach?
Yes, so I didn't show this comparison here. I think maybe I have an extra slide. We did. Is it this one? So we did spurious currents for translating drops. I mean, for static drops, we never die for CSF or for our method, which is CSS, but for CSF we die because the spurious currents die, not we, to the machine accuracy, because it's well balanced. Whereas in this case, you can see like the spurious currents, which is, I think, yeah, so this is the CSF method, this is CLSVOF. So it's in WOF, CLSVOF, it's already less as compared to the CSF method, whereas in HF2D it's larger, and but then they grow in this method, they don't grow in this one. And then in HF it's really bad, the spurious currents grow very quickly to very large values. Yes, assuming a static interface, CSF would be better.
the gain of the initial
Which one?
the view in the inkjet printer?
Ah,
The pink.
up. Played. Yes.
So I saw this movie at the ATS 1 year ago, and it was really fascinating because I said it works so well. And then I was thinking, are you just lucky here that you see no instability, no oscillations, smooth motion of the contact line, or is it maybe due to the choice of parameters such as?
I think it's due to choice of parameters. There are problems very close to contact line for sure, but it's just that we try to choose parameters and stay in a regime where things work in terms of capillary number. I would say. I think it should be known because there is a velocity. I know that there is a velocity somewhere. Because we use water properties and then we have yes, and then we have this velocity which is so 14 times u. So u is around 1 micrometer per second. So you get a capillary number which is very high actually. So it's 10 micrometer per second the velocity scale, and then water properties for gamma and mu. So you get, I think, plus. Thank you.